Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from learned hand. Life is made of series of judgments on insufficient data, and if we waited to run down all our doubts, it would flow past us, right. You need not be too worried about like the things, but however you should take a conscious decision before doing something. So, that is the meaning of this. So, in the last lecture what we did, we basically looked at the governing equations for the laminar and two dimensional unsteady flow, later on steady flow, right, we consider, and we looked at little bit about boundary layer very briefly, but I would suggest that we may not use very much in our course, but however some touches or some feeling you should have. And very important that we derived a what you call equation, one dimensional equation of course, for mass mixture fraction, right, mixture fraction governing equation, which is basically a conjugate scalar. So, and those equations is valid basically for laminar flow, and keep in mind that we will have to deal with what you call the also turbulent, and laminar flow means the flow will be layer by layer. If you look at this is being shown here, in this case is a flow through a pipe, right, it is a layer by layer. That means there will not be any mixing across the thing, but whereas in the turbulent, right, the flow will be not layer by layer, it will be intermingling with each other, right. Are you getting? So, therefore, we need to look at that, and turbulent combustion plays a very important role. Why? Because the most of the combustion devices is basically turbulent in nature, except few exceptional cases, right. For example, if you consider your LPG burner, is it laminar or turbulent combustion? It will be, it looks to be laminar, but if you look at the candle light, is it laminar or turbulent or transition? What it would be? It will be not laminar, it will be basically transition, right. So, but most of the combustion system in industries, namely gas turbine, piston engines like furnace, extra, are turbulence, and it helps in mixing process between fuel and oxidizer. Why you will go for turbulent? Not only the mixing, we want to have a high rate of heat release. That means mixing should be as fast as possible, right. Therefore, we need to go for turbulent combustion. If you look at this is IC internal combustion is, these are the combustion taking place, and if you look at this is intensely mixed, right, that means the combustion will be turbulent. And this is your gas turbine combustors, right, where it is having a lot of mixing is going on, and there is also some injection fluid like secondary airflow is coming over here, and then let us look at this is a coal combustion, which is a pulverized means particles, right, and combustion is taking place. What you could observe the characteristics feature of a turbulent combustion. Let us look at the a combustion from a blob body. stabilized flame, of course, you might be knowing the blob body is being averred in fluid mechanics. Am I right? Always you want to have a streamlined body, isn't it? In aerodynamics, other places, but in combustion we will be using blob body. Why? Because we want to have a mixing, better mixing, whichever the disadvantage in fluid mechanics, and it will be using as advantages, So, and this is the combustion which will be taking place and which is quite convoluted and turbulent in nature. Now, therefore, it is very important to look at the fundamentals of combustion. What I will do, I will be only touching upon certain terminologies we may use. Okay, I will be not getting detail into that, and so can we define turbulent flow like the way we define the laminar flow? How we do? Right? There will be some characteristics. The flow will be layer by layer, and then we can say whether it is laminar or turbulent, right? Kind of things. But can we define turbulent flow? And we use the viscosity, like diffusivity, mass diffusivity or molecular diffusivity and other things. Those are properties of fluid. Which one? Isn't it? Like if I will say it is air, the viscosity will be different. If I say water, it will be different, right? But whether we can define the turbulent, you cannot really define the turbulent flow. You will have to describe the turbulent flow, right? And now, how we will describe the turbulent flow? That means we will have to use some characteristics. What are those characteristics? Any idea? Huh? It will be irregular, right? It will be, that means the flow will be convoluted, it will be mixing, that means there will be intervening of the fluid element or the bulb which will be taking place, right? The molecules will be moving here and there, and there some fluid packets will be moving up and down in the adjacent layer, right? And as a result, if I consider, right, a jet, let us say, if I look at this is my air jet and there is a flame here, right. If it is laminar, my flame will be looking like that, if it is laminar, some shape, particular shape, but if it is turbulent, right, it will be like that, some kind of, it will be intermingling surfaces, and this is each one of this instantaneous contours. Contours of flame. So, this will be here my average flame surface, right, and these will be very irregular in nature. But if you say, look, I have taken a photograph of the flame and it looks to be very smooth, it is not, because it will be averaging out, you will not see it unless it is highly turbulent. And this flow will be 3-dimensional in nature. You cannot say I will consider 2D, okay. It will be 3-dimensional in nature and rotational. Rotational means the fluid will be rotating, in the sense, rotational flow, like inviscid flow is rotational or irrotational? That will be irrotational, right. But here it will be rotational. You cannot really consider inviscid, then turbulent. Can you consider? No, no. So, and as a result, there will be higher diffusivity. What do you mean by that? We have seen various diffusivity like conductivity, thermal conductivity, molecular diffusivity, right, and viscosity. These are all diffusivities, right. So, those will be much higher than the molecular one. Are you getting? And it will be diffusing, moving around, intervening kind of things. And of course, we always use a Reynolds number to say whether laminar or turbulent or transition, right. That is a what you call high Reynolds number, generally known as the turbulent flow. And as we had defined earlier, basically that is Reynolds number. With d by mu, if d is the diameter of the tube, this is your diameter, right, diameter of a tube, this is a tube, right, from which the flow is going out, right, both fuel or air mixture you can say. And question arises whether it is a continuum or not, because all our mixing is taking place, will you call it as a continuum or a not continuum? It will be definitely coming under continuum, because there will be intense mixing is taking place. It is not that the mean free path is far away from each other, it is the far greater than the length scale of the where it is moving, length of the other flow. So, therefore, it will be continuum in nature. And now, how to deal with that? Because as I told, in this image or this flame, there will be the flame surface or the velocity or the temperature or the spaces, right, mass fraction will be all changing rapidly with time, right. Now, how we will deal with that is the question. Before doing that, let us look at how we can describe. Basically, as I told, turbulence is not a feature of the fluid. I have already told, like diffusivity, molecular diffusivity, conductivity, and then what you call viscosity. These are all properties of fluid, not properties of the flow. Okay? And keep in mind that if the Reynolds number is quite large, of course not in the transition regime, the turbulent flow is not controlled by the fluid properties, rather flow features. It will be how the flow it is. And now we will be looking at how we will take care on some of the terminology. I will be talking about it. So, at high Reynolds number, like properties like velocities, temperature, mass fraction exceeds random variations, right. Now, how we will deal with it? Because if it is varying randomly, then we will have to use some statistical tools, or we will have to make some average quantities. And keep in mind that ADs move randomly back and forth across the adjacent layer. Let us say there is a bulk fluid which is moving, but in between it will be also moving the fluid elements. Unlike in laminar flow, where the flow will be moving very nicely. See, if you look at turbulent flow, you can look at your traffic in Kanpur. All these cars will be not in a lane, they will be not following lane, they will be moving here and there the way they want. Are you getting? In Kanpur of Kanpur, right? But if you go to the western country, the car will be moving in their own path taking. So, it will be laminar, but here we will be moving here and there. So, it will be losing a lot of energy, and also it will be causing some problem. So, but there is, as a result, of this fluid moving in the in a turbulent way or chaotic way, I can say, like all turbulent flow need not to will be chaotic, but all chaotic flow need not to be turbulent. There will be enhancement of mass, momentum and energy transfer rates. So, that is why it is being used. And now, what we will be looking at, let us look at a velocity profile, velocity fraction along with time V x. If you look at, this is your average velocity V x, and this is V x at any instant of time. If I consider this as, let us say, this is straight line, as t naught, this will be V x dash at t naught. At some other time instant it will be different. This is the fluctuating quantities, this is the maximum or you can say fluctuating quantity. That means I can write down that V x, it would be what? It would be V x at any instant of time, right, is equal to V x dash, that is average velocity along with the x direction, right, and V x dash is the fluctuating quantities. So, what is this V x dash? If I look at, that is nothing but 1 over delta t, t1, t2, this is V x over time dt. If we integrate over the certain time, which is a very large time scale, right, it is not a very small. If you should not consider only this portion, you should consider certain considerable time, then this is the average velocity, and there will be of course fluctuating quantities you will be looking at. And similar way, I can also talk about what you call pressure, Pt is equal to P and I can talk about this temperature also, dash T, and similarly mass fraction of is species dash of T, and this is basically known as what you call Reynolds decomposition. Having two component, one is fluctuating, other is average quantities. And if you look at that, when you will do these things, right, you will find, as I told earlier, that in terms of when you will consider the laminar and the velocity over a flat plate, we can look at as basically this is a laminar velocity profile and this is a instantaneous turbulent velocity profile, this one, right, this fluctuating one, and this a smooth line is basically turbulent time average velocity components, right. And as I told that when we will consider, because we will be more interested in the what you call diffusivity terms, right. I am not going to derive, it is a very Reynolds an average this thing, you will have to look at this equation, carry out this, but I am just writing, and then each governing equations and then look at it what it would be, but I am just writing the final expression just to say that how it will be different, and it will be similar in format of the whatever we have derived for the shear stress and then heat flux and the mass flux kind of things. So, turbulent diffusivity for momentum and also the thermal and also the mass diffusivity for for mass, momentum and energy is given by tau t is equal nothing but a rho Vt and Vx average by dy. Right. Keep in mind that this Vt is the what you call turbulent viscosity. Similarly, I can write down as rho Cp alpha T I can write down d actually, this is better, okay, d by dy. Similarly, A species I am saying turbulent would be rho d T keep in mind that this is your thermal diffusivity, thermal turbulent and keep in mind that this thermal turbulent diffusivity or turbulent viscosity or this is turbulent mass diffusivity, they are properties of the flow, you will have to connect that, right. And this we will be not considering, but let us look at how we can really describe these properties, like how we can describe these things using various terms. So, if you look at turbulent flow can be characterized by two quantities, one is turbulent intensity, right, and another is the turbulent scale. Right. If you look at here, this is basically a jet which is ejected from here and it is a turbulent in nature, and these are all lobes, right. And there will be also there will be rotation of fluid here, and then some elements of the fluid will be intervened and it will be rotating, right, with the vortices, and those vortices will be having some identity, right, certain identity. That means the microscopically they will be rotating, but they will be together in macroscopically, right. That we call it basically as eddies, right. So, an eddy is considered to be microscopic fluid element in which microscopic element comprising of eddies as a single unit. That means there will be some small eddies which will be rotating as a unit, right. For example, if you look at, there will be various panth in the Sanatan Dharma, right. Let us say some group is talking about yoga, somebody is talking about bhakti, right. They are also having some kind of thing, they will be rotating, they are moving around it, but they will be having similar in nature. So, that we call it as eddies. Are you getting? So, that means some fluid element will be moving, let us say here, I mean if I consider let us say in this bulb, right, I can consider as this one, right, they will be moving, rotating, and they will be intermingling, intertwining, but they will be in a group which will be doing, and that is known as a eddy. And as I told, the vortex embedded in flow, this is basically a vortex, right, which is embedded in the flow. Vortex means which will be rotating, right. And the intensity of the turbulence is basically measure of violence of eddies. So, how fast it is moving, so that energy is transferred, right. So, that is known as turbulence intensity, and turbulent intensity will be dependent on what? Basically fluctuating quantities. And if I say that Vx dash, fluctuating along the x direction, and V dash y in the y direction, then and Vz dash in the z direction, but it is fluctuating with respect to time, then all these square together divide by average, it will be known as intensity. It can be also put in terms of percentage, right. Turbulence index 10%, 5%, 20%, you know. If you go for a wind tunnel, generally low turbulence means it is a better, right, inlet, but you can create some turbulence to study what is happening to the turbulence level, right. So, turbulence intensity is also looked at that way, by which we can characterize, and there is a length scale of turbulence, right, which is can be defined as the distance covered by AD before it disappears or loses its identity. But what is happening, let us say some fluid is moving here, and then as it moves it will be merged with these stops. So, that will not be there, right. If it is going with respect to time, let us say it is moving with respect to this, when it moves then it loses its time. So, that is the length scale, what will be, how much distance it will be lost its identity, distance covered by an AD before it disappears or loses its identity. That means in between it will be keeping it identity, right. And that distance is known as the length scale. Length scale will be what you call divided into basically 4. One is microscopic length scale, which is the characteristic width of a flow. Let us say if it is a pipe flow, what you do with the microscopic scale for pipe flow? For pipe flow, what would be? L will be basically d, diameter of pipe, right, and there is a integral scale L naught, and there is a Taylor microscale and Kolmogorov length scale. Keep in mind that this is of course mechanical, that we use this microscopic scale for laminar flow, we always use low BD by mu to find out Reynolds number. But in turbulent flow you will be using different scales to find out different kind of, you know, Reynolds number. And keep in mind that these scales will be changing, that because AD's size will be changing and the time, the distance it will be moving before it losing its identity also will change. So, therefore, scale will be changing, and keep in mind there is a cascading effect, that means larger scale ADs become smaller and smaller and smaller. The lowest one will be Kolmogorov length scale, which is the dissipation, because it will be dissipated. After that it is a very very smallest scale is the Kolmogorov microscale, right. So, let us look at the what you call the integral scale, right. L naught, as I told, L naught is the integral scale, and this basically represents the distance between 2 points in a flow where correlation between the fluctuating velocities between two locations are ceased. That means there will not be any correlation between. For example, if I say there is a fluid element, you know, having some kind of the what you call velocity fluctuations, right, and then it is having some distance, you know, there is another between which it is having, let us say, distance r, right. So, this will be moving, let us say Vx, this is at 0, right, at 0, and this will be Vx dash at r. That means there will be some correlation between the two, and that distance will be telling you the integral scale. So, L naught, that is the integral scale, I can write down 0 to infinity r x r dr, right, and Rx is the correlation coefficient, right, and as I told, this is basically function of what you call function of the distance, right, between which the velocity fluctuation will be losing its identity. So, I can define this R x, R is basically V x dash at the time is R is equal to 0 and V x dash at R is average over the both the thing divided by V x RMS dash 0 and V x RMS dash R. So, this is basically the correlation coefficient which you need to look at it to define the length integral scale. Similar, I am like in another way we can talk about the Taylor microscale L dash, which is nothing but V x dash RMS divided by dou B x by dou x, average of that into square is known as the mean strain rate. This is basically mean strain rate, right, and divided by that will be giving you the Taylor microscales. And the Kolmogorov scale is 2 nu q L naught divided by 3 V RMS cube power to the 1 by 4, and this is by order of magnitude analysis people have come up, and this is related to basically integral length scale. This is L naught and also the VRMS, and this nu is basically the turbulent what you call viscosity, right. You can say this is T, and LK as I told is the smallest vortex that could be present in the turbulent flow. After that what will happen? It will be dissipated, right. This will lose its identity altogether. That means all these things, energy which will be carrying by this vortex will be lost. Are you getting? These are all packets of what? Energy which will be carrying by the vortex, and which you call AD. Now, based on this you can define various kinds of Reynolds number, okay, based on these scales. So, that is turbulent Reynolds based on the length scales, and this is your REL and this is your macro scales, right. This what we call is basically macro scales, macroscopic scales, and V RMS L divided by nu, and this is what we call, generally we call Reynolds number in a laminar flow kind of things. But in turbulent flow, depending on the situation which we will be using certain cases, this is Reynolds number based on the integral scale. Only difference is that what you are using L naught, right, and of course here using V dash RMS, right. RE L lambda is nothing but V dash RMS L lambda divided by nu, and LEK is nothing but V dash RMS LK by nu. So, keep in mind that V RMS is the characteristics velocity in the turbulent flow what we consider, and that is a root mean square velocity. This is characteristics root mean square velocity, root mean square velocity, right. So, with this brief introduction about turbulent flow, I will stop over here. In the next lecture we will be discussing about basically about the combustion. So, keep in mind that we will have to also look at some of these terminologies whenever you will go for turbulent premix plane. Thank you very much.